Okay, A-level physics, paper 2. So how do we make this transformer more efficient? Okay, so hope you're thinking transformers, we know we see them in power stations, okay? So transformers is a way that we can change the potential difference. And hopefully the reason why I'd want to change the potential difference, and we can tell from looking at this transformer that it is a step-up transformer. I know it's a step-up transformer because it's got more coils of wire on this secondary arm. This is my primary arm, this is my secondary arm. So a step-up transformer, the whole reason is to increase the potential difference. Now why I'd want to do that is because I know that I have these cables carrying electricity around the national grid to my home where I am. Now the power station people, they don't want to lose money. So when they transmit this electricity for these cables, they want to make sure the current in the cables is as low as possible. Because we know in the cables, if the current, when there's current flowing through them, because of the resistance of the cables, we know there's going to be some power loss, some energy loss. And that power loss, P is equal to I squared R. So R is my resistance of my cable. I is the current through them. So if we keep that current as low as possible, there'll be less power lost in my cables, right? Because we know power is going to get lost due to heating. So the way to get the current as low as possible is to make the potential difference as high as possible. Because again, we know the power station is going to output a certain amount of power, and P equals IV. So this power that the power station outputs, that's fixed. So if I make the potential difference as high as possible, that's why the current in my cables becomes as low as possible. Okay, so how to make these transformers really efficient so that we can get all of the power basically that goes in to all the power that comes out, right? How do we make it like nearly 100% efficient? So things we want to do is we want to make sure that the core is made of soft iron. And the reason we make it from soft iron is because soft iron can be easily magnetized and demagnetized. Okay, so things we can say is, again, we're going to make it of soft iron. Because we know, if I can spell iron, because iron can be easily magnetized and demagnetized. Okay? If you're finding this type of stuff helpful, remember we've still got exam masterclasses. Exam masterclasses, we're giving you 15 hours of content revision for only 59 quid. We've already started them, and we're all the way through our learning. We had an amazing paper 1 session the other day. But if you want to join us, click in the bio. And remember, you can still get recordings. So you can just get those last recordings. Okay, so magnetized and demagnetized. Other things we can do is we can laminate the iron core. So what that means is we put these layers of insulation in the iron core. So again, what we do is we want to laminate the iron core. So we're going to put those layers in there. And the reason we do that, the reason we put those insulation layers in there, because if you think about it, what we have here is we get current in this primary coil, okay? We get current in this primary coil, and alternating current is changing current. We know that anytime you've got current for a wire, you get a magnetic field. So what I've got is a change in magnetic field in this core, okay? So a change in magnetic field in this iron core. What's going to happen is we're going to get some induced EMF in the core. And we get these things then called eddy currents, so just like little loops of current. So we don't want these eddy currents to form. Okay, so we don't want the eddy currents. That's why we put these layers of insulation around the transformer to try to stop the eddy currents form. So we laminate the iron core in order to reduce the eddy currents. So eddy currents is, again, just what we call like little loops of current that happen in the transformer. We don't want them there. Okay. One more thing I've seen in a past paper question is talking about the frequency that comes in here. Okay, because we know due to Faraday's law that the EMF induced is equal to the rate of change of that magnetic flux. So magnetic flux, that's B times A, just how many magnetic field lines are passing through an area over a time, okay? So clearly that the faster, so the smaller this number is, okay, the smaller time it takes for a full oscillation, the bigger the EMF is going to be. So the smaller time it takes for an oscillation, what we're trying to say is a lower frequency. It means we're going to get, pardon me, the smaller time, the less time it takes for a single wave, means we're going to have a higher frequency. So the higher frequency means we're going to get a bigger EMF. So we don't want these eddy currents in my transformer. So a way to get a smaller EMF in the transformer is to use the opposite of this to get a bigger time, a lower frequency. So what we could do is we could use a lower frequency of my alternating current. Okay, because remember, the voltage in this secondary coil, depends on the voltage in the primary coil, and it's dependent on the ratio of the number of turns of wire in each arm. Okay, so that's why the frequency there is just affecting those eddy currents. That was a cheeky multiple choice question in a past paper. So we have a lower frequency, we're going to get less of these eddy currents because there'll be a lower EMF. So hopefully you find this helpful.